So this question requires us to use a polynomial with at least 3 terms. So this polynomial has more than 3 terms because it has the leading coefficient, the second term, the third term, and the constant. So we can check that off. It has a positive leading coefficient of x to the power of 3. It has a degree of at least 3 because the highest degree of this polynomial is 3. And we can use long division to verify whether this polynomial has 3 real roots. In order to find all real roots of this polynomial as factors, we must first list the factors of the polynomial's constant term as positives and negatives. In this case, the constant term is 10, so we are going to list the factors of 10. So that's plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. They must be factors of a constant term because the LC is equal to 1. And the factors must be made in the form x minus b. This is all a part of the integral 0. Our second step is to choose one of the factors of the constant term 10 and convert it from the form x minus b to the form x is equal to b. So I'm going to choose the factor negative 1. So originally this is in the form x minus 1 is equal to 0, which means that when we convert it, it becomes x is equal to 1. B represents the value that we will substitute into the polynomial. In order for one of these terms to be a true factor of the polynomial, the sum must be 0 after its placement into the equation. Repeat this process until you find a factor of the constant term that gives a sum of 0 if your first choice doesn't work. So we're going to substitute 1 into where x is, which gives us a result of 1 minus 4 minus 7 plus 10. When you calculate this, we know that P1 is equal to 0, meaning x minus 1 is a factor of the polynomial. This process of using factors in the form ax minus b or x minus b and subbing them into the polynomial is known as factor theorem. Once we get our first factor of x minus 1, we can use it as the divisor and divide the original polynomial. In order to complete long division, we see how many times x needs to be multiplied in order to get x cubed. So that means x squared. We multiply x by x squared, and that gives us x cubed again. So we subtract these two numbers. Then we take negative 1 and we multiply it by x squared. So that gives us negative x squared. We subtract these numbers, and that gives us 0 and negative 3x squared. We bring down the extra term and its sign, and that becomes negative 3x squared minus 7x. We then repeat this process until we get a full quotient on the top, and the polynomial can no longer be further divided. After completing long division, we find out that our quotient is x squared minus 3x minus 10, form of a quadratic. So our quotient was x squared minus 3x minus 10. We can find a number that adds to negative 3 but has a product of negative 10. So that would be positive 2 and negative 5. We can write that factor in the form x minus 5, x plus 2, coming from these two numbers. Then, this means that x minus 2 and x plus 5 are factors of the polynomial. And going back to our original polynomial, 2 and 5 are both factors of 10, which was our constant term. Therefore, the factors of the polynomial are x minus 1, x plus 2, and x minus 5, which means it was a correct polynomial because it had 3 real roots. This question requires us to use a polynomial with at least 4 terms, a negative leading coefficient, a degree of at least 4, and at least 2 real roots. We know that there are at least 4 terms because we have a quartic equation. It has a negative LC because our 2 has a negative sign, which is our coefficient, a degree of at least 4 because the 2 has a degree of 4, so we know that that applies. And to figure out whether this equation has 2 real roots, we're going to find the solution to the polynomial. In order to find the solution to px is equal to 1, like the previous time, we must list the factors of the constant. But this time, because the leading coefficient is greater than 1, we must also list the factors of the leading coefficient. We list both factors and then list all possible factors by doing both of these factors as well as the factors of the leading coefficient over the factors of the constant. We then choose one of these factors. In this case, I chose 2, and I substitute it into the equation. I get Negative 32 plus 192 minus 416 plus 384 minus 128, which gives me a sum of 0. Therefore, we know that x minus 2 is the solution to the polynomial. After our first step of finding the solution of when px is equal to 0, like in the last problem, we then complete long division once again. So we see how many times you have to multiply x to get negative 2x4 and write the answer in the quotient section. You multiply negative 2 by this number, and you write the sum here. So then you subtract, and you bring down your numbers. After following this process over and over again, you then have your quotient, meaning the equation we now have to work with is negative 2x cubed plus 20x squared minus 64x plus 64. We're then going to factor this equation. With our quotient, we then repeat steps 1 and 2, where we find when px is equal to 0, which is at x minus 2 for this polynomial, and we complete long division once again. The quotient for our next long division, using x minus 2 as the divisor, is 2x squared plus 16x minus 32. This is a quadratic, so our third step is now to factor. Our equation is now 2x squared plus 16x minus 32. By factoring out a 2 in the second term, it gives us negative 2x squared minus 8x plus 16. As you can see, this is a perfect square, which will factor out as x minus 4 squared. Therefore, our equation is now negative 2 x minus 2 squared x minus 4 squared is equal to 0. Therefore, the solution of px is equal to 0 is x is equal to 2 or x equals to 4, as they will both give us value of 0 when substituted into this polynomial. So, what is remainder theorem? The purpose of remainder theorem is to allow you to determine the remainder of a function when divided by a polynomial in the form x minus b or ax minus b without having to go through the steps of long or synthetic division. Remainder theorem states that if you start with a polynomial f of x and you divide it by a linear factor such as x minus b or ax minus b, then the remainder will always be equal to f of b or f of b over a, respectively. You can use remainder theorem when trying to find the value of a function. All you need to remember for this theorem is that the value of the divisor at its root will always be the remainder of the polynomial. Here's an example that can be taken of remainder theorem. We start with this polynomial and divide it by x plus 9. Our first step is to find the root of divisor. So in the format x minus b, x plus 9 is equal to 0. So when we isolate, we know that x is equal to negative 9. We substitute negative 9 into the polynomial, and once we find the product and the sum, we know that the remainder is going to be equal to 19. If we were to do long division on this polynomial, the remainder would also give us a value of 19. For polynomials with a leading coefficient equal to 1, sometimes factoring by grouping does not work. Another method of finding the factors of the polynomial can be done by substituting values in the form b or b over a into the equation. In this example, this polynomial has a leading coefficient of 1 and a constant term. So we know that we can do the factor theorem. The first step to solving this polynomial is to find the factors of the constant 3. This gives us plus or minus 1 and plus or minus 3. If the value of the polynomial at pb is equal to 0 or p over b over a is equal to 0, then the number that you substituted is one of the real roots. In this example, we can substitute 1 into the polynomial, which, when we do the math, gives us a value of 0. Therefore, using factor theorem, we are able to tell that x minus 1 is a factor of this polynomial. When the leading coefficient of a polynomial is greater than 1, rational zero theorem is used to find the roots. To use the rational zero theorem, we look at the constant term of the polynomial and the leading coefficient. In this example, the leading coefficient is 5, so the factors of 5 are plus or minus 1 and plus or minus 5. The factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. Then, we can use the factors of 4 over the factors of 5 to get all possible values for this polynomial. So that gives us plus or minus 1 over 5, plus or minus 2 over 5, and plus or minus 4 over 5 as the other factors of this polynomial. Polynomials with the leading coefficient greater than 1 will always have a root in the form of x equals b over a. Rational zero theorem states that the b value will always be a factor of the constant term, and the a value will always be a factor of the leading coefficient.